I want you to step into a highly specific, totally immersive scenario with me for just a moment.
Oh, this is a good one.
Yeah, so close your eyes. Well, unless you're driving, obviously. Imagine you're sitting in one of the world's truly grand concert halls. You know the kind I'm talking about.
Right, with the plush seats and all that.
Exactly. The seats are that dark crimson velvet, the kind that feels like it's absorbed a century of standing ovations.
Mm.
The air in the room has this heavy, expectant quality to it.
You can just feel the history in those rooms.
You really can. And you could hear the hushed murmurs of like a couple thousand people settling in, the rustle of heavy paper programs, and drifting above all of that is the chaotic, beautiful sound of a world-class orchestra just tuning their instruments.
Right, it echoes off all that ornate wooden acoustic paneling.
Yeah, wrapping right around you. So the orchestra is settling in, and tonight they are playing Beethoven's Fifth Symphony.
Which is, arguably the most recognizable piece of classical music in the history of human civilization. The cultural weight in that room is just immense.
It really is.
Yeah.
But I want you, the listener, to picture something fundamentally different about this specific audience. Scattered throughout the crowd, sitting in those velvet seats, are several members who are completely deaf.
Wow. Okay.
And they are wearing these sleek, lightweight AR, augmented reality glasses.
It's such a striking image to conjure up. You have this ultimate juxtaposition, right?
Yeah, totally.
A centuries-old acoustic tradition performed on instruments carved from wood and brass using techniques passed down over hundreds of years.
And it's colliding seamlessly with absolute cutting-edge, wearable spatial computing.
Exactly. It's wild to think about.
And here is the exact moment I want you to visualize. The conductor walks out from the wings, the applause swells, and then it fades.
Yeah.
He steps onto the podium, raises the baton, and the hall goes dead silent.
You could hear a pin drop.
Right. And as that baton comes down for the downbeat, as the orchestra delivers those legendary, world-shaking first four notes, the silent world of those deaf listeners in the audience absolutely erupts. It doesn't just vibrate the floorboards. Their visual field explodes into this meticulously choreographed cathedral of shape, color, and text, unfolding in real time right before their eyes.
Right, floating literally in the physical space above the orchestra.
Exactly. And that is the whole mission of our deep dive today. We are going to explore exactly what those deaf audience members are experiencing visually and tactilely during the symphony.
And the word choreographed is really the crucial operating term there.
Why is that?
Well, because the immediate assumption people make when they hear music visualized in AR is that it's going to look like a random psychedelic light show.
Oh, like those old computer visualizers.
Right. If you grew up in the late 90s or early 2000s, you're probably picturing a Winamp visualizer.
Yeah.
Or a screensaver that just flashes chaotic colors whenever there's a heavy bass beat.
Yeah, just totally random shapes.
Exactly. But this is the exact opposite of that. What these listeners are experiencing is a rigorous, mathematically precise, highly intentional translation of musical structure.
So it's actually mapping the intent of the music.
Yes, mapping the harmonic tension and historical intent entirely into a spatial, visual, and tactile language.
That is just incredible. We aren't stopping at just the experience today. We are going to peel back the layers of the technological engine room that makes this synesthetic miracle actually possible.
The tech stack behind this is fascinating.
It really is.
Yeah.
Honestly, looking through the sources, I was blown away to learn that the architecture making this happen tonight spans all the way from 1980s Apple II software to hyper-modern WebXR rendering engines.
It really is a sweeping narrative. We are looking at a 40-year evolution of how human beings represent music as abstract data.
Taking pure logic and turning it into light.
Right, translating it through the unpredictability of human time and rendering it as physical mass in a three-dimensional space.
Okay, so let's step into the shoes, or rather put on the AR glasses of our deaf listener in that hall.
Let's do it.
The symphony begins. Da-da-da-dee-um. For a hearing audience member, those four notes shake the room. It's a literal auditory gut punch.
Oh, absolutely.
But for our deaf listener, as that baton strikes, this legendary opening motif appears in their field of vision, anchored perfectly over the stage as this stark, dramatic, razor-sharp geometric spike.
And that stark spike introduces us to the foundational layer of this entire AR experience, which the developers call the thematic recognition system.
Thematic recognition system. Okay, break that down for me.
To understand why this is even necessary, you have to think about how human hearing works. Human ears and the auditory processing centers of our brains are naturally incredibly gifted at pattern recognition.
Like recognizing a catchy chorus.
Right. If you hear a melody at the beginning of a movie and then hear it again 2 hours later, played on a totally different instrument, say at half the speed in a different key, your brain instantly connects them.
You're like, oh, that's the Darth Vader music.
Exactly. You recognize it as the villain's theme. But visual translation is much trickier. If you just translate raw audio frequencies to shapes, the visual of a slow flute playing a theme will look absolutely nothing like a fast cello playing that same theme.
Ah, I see. Because the frequencies are totally different.
Right, so the visual system requires an equivalent cognitive anchor.
Okay, so when that identical four-note fate motif returns later in the piece, say in the much slower second movement, the AR system doesn't just generate a generic, random pulse of light based on the current volume.
No, it doesn't.
It deliberately brings back that exact same geometric spike.
Exactly. It creates a visual family resemblance, but it doesn't just copy and paste the visual from the first movement. The visual mutates because the musical context has mutated.
Right, the vibe is different.
Exactly. In that slow second movement, the music is lyrical, it's thoughtful, so the AR system renders that familiar geometric spike, but visually softened.
So the sharp edges are gone.
Yeah, the aggressive edges are blurred. The physical form is elongated, reflecting the slower tempo and the smoother articulation of the string players.
Wow.
So the architecture of the shape is identical, meaning the listener's brain registers the theme, but the texture of the shape tells them the mood has shifted.
It's kind of like running into a friend you haven't seen in a decade. You instantly recognize their facial bone structure. That's the core theme.
That's a great analogy.
But the wrinkles around their eyes, the way they carry their shoulders, their posture, all of that tells you the story of what they've been through since you last saw them.
Exactly. You recognize the core identity, but you perceive the evolution. And to finish that thought, when we finally reach the triumphant, blazing finale of the Fifth Symphony and that theme comes roaring back in a major key, the spike returns in the AR glasses.
But it looks different again.
Yes. Now it radiates outward. It fills the surrounding visual space with this brilliant golden light. The system is allowing the deaf listener to literally trace the biographical arc of a musical idea over a 40-minute journey.
That is just beautiful. Okay, so I understand how a specific melody is treated. But when I look at a symphony orchestra on a stage, I'm looking at like 70 or 80 people.
Right, it's a huge group.
Just a sea of performers in black formal wear holding pieces of wood and brass. Now, for a hearing person, our ears naturally mix the sound. We can pick out the solo violin soaring over the heavy cellos.
Humans are great at audio filtering.
Exactly. But if I'm looking through these glasses, how does the system prevent the visual from just being a chaotic, blinding soup of glowing colors?
That's a really common issue in AR design.
Yeah, like how do I know where to focus my attention if everyone is playing at once?
So that is solved by a concept in the rendering engine called voice highlighting. The system effectively transforms the orchestra from a static, uniform group of people into a glowing, dynamic map of musical hierarchy.
Musical hierarchy.
Yeah, it solves a massive problem for untrained listeners, honestly, whether they're deaf or hearing. In a dense, complex orchestral piece, the primary melody can easily get buried under everything else going on.
Oh, for sure. Sometimes I get totally lost at concerts.
Right, so the AR experience dynamically assigns subtle luminous halos around specific instrument sections, and it bases this entirely on their structural importance at that exact millisecond.
Okay, walk me through what that looks like in practice.
Yeah.
If the violins are playing the main melody, what do I actually see?
If the first violins have the primary melody, their section on stage glows with a warm forward-sitting luminosity. It naturally draws your eye right to them.
Okay, and what about the rest of the orchestra?
Meanwhile, the instruments providing the harmonic foundation, say the double basses, they emit a gentle, steady, grounding pulse of light. It's visually heavier, but it's less bright.
Gotcha, so it's not distracting.
Exactly. And then you have the counter melodies, the inner voices, like the violas or the bassoons, playing a secondary tune that complements the main one. They shimmer at a lower luminosity. They are visually present in the mix, but they recede.
So it's basically a live-action, three-dimensional mixing board for my eyeballs.
That's exactly what it is.
I can choose to focus my gaze on the glowing violins, or I can actively decide to look over at the shimmering bassoons to see what the secondary characters are up to.
Yes. And perhaps the most elegant feature of this voice highlighting system is the anticipation mechanism.
Anticipation.
Yeah, a huge part of the live musical experience is the physical tension of a performer about to play. You know, a musician takes a massive physical intake of breath before blowing into a trumpet. A violinist raises their bow.
You can feel the energy right before they strike.
Right, and the AR system replicates this breath. Because the system knows the score in advance, when a section of the orchestra has been sitting completely silent for 100 measures and is finally about to enter, the glasses generate a gentle pre-glow of anticipation over those players.
I absolutely love that. So before the brass section even makes a sound to deliver a massive chord, my eye is naturally drawn over to them.
Yes.
The glasses are essentially whispering, hey, look over here, something big is about to happen.
It beautifully replicates the physical intuition that seasoned concertgoers develop over decades, but the system has to go beyond just pointing out who is playing. It has to visualize the abstract architecture of the music itself.
You mean the harmonies and the dynamics?
Exactly.
Right. And if you aren't someone who spent 4 years in a music conservatory, terms like harmonic tension or dominant seventh chords just sound like academic jargon.
Oh, completely.
Yeah.
It's totally opaque to most people.
So how do you visualize something as abstract as a feeling of tension?
The designers of this AR experience made a brilliant choice here. They map harmonic tension directly to the listener's peripheral vision.
Wait, the periphery. Not right in front of them.
No, and it relies on a deep understanding of human biology and perception. Think about how your eyes work. Your foveal vision, the dead center of your sight, is for sharp, high-resolution details. Reading text, recognizing faces.
Right, focusing on things.
But your peripheral vision is incredibly sensitive to changes in light, motion, and color over a wide area. It processes atmosphere.
Oh, that makes so much sense. So they aren't forcing you to stare directly at a glowing orb of tension in the middle of the stage.
No, because that would completely distract from the performers. Instead, stable harmonies, what musicians call the tonic or the home base of a piece, are rendered as warm, settled amber tones that pool at the very edges of your visual field.
So it feels cozy.
Yeah, it feels like you are sitting in a room with a crackling fireplace. It feels like solid ground. But as the music begins to build towards dominant tension, which is the harmonic feeling that the music absolutely needs to resolve back home.
That environmental color field in your periphery begins to shift.
Yes. The space slowly turns into a pressurized blue-green.
Pressurized is such a visceral word in the sources. How does a color feel pressurized?
It's achieved through subtle pulsing and an increase in visual density. It creates an almost physical sensation of holding your breath. You aren't staring at the blue-green light, but it alters the entire atmosphere of the room.
I can almost feel that just thinking about it.
And when the music gets highly dissonant, when notes are clashing and rubbing against each other aggressively, the AR system introduces fractured, slightly uncomfortable, sharp visual textures into that peripheral space.
It actively makes you feel visually anxious.
Yes. And the payoff is magnificent.
Yeah.
Because when the orchestra finally resolves that clashing dissonance back to the home key, back to the tonic, there is a visible exhale in the AR space.
Release.
Exactly. The fractured textures dissolve instantly, and those warm, settled amber colors flood back into the periphery. You physically feel the relief.
Okay, so that covers the harmony. But what about sheer volume? The dynamic range. Because a deaf listener isn't getting the physical eardrum assault of a fortissimo brass blast, nor the absolute quiet of a pianissimo violin whisper.
Right, the extremes of sound.
Yeah, so how do the glasses communicate volume?
The system renders volume as physical mass and weight within the three-dimensional space. A loud, massive, heavy chord played by the entire orchestra literally looks like a towering, dense mountain of geometry in the visual field.
So it actually looks heavy.
It takes up space. It looks incredibly heavy. Conversely, a very quiet, delicate passage played by a few strings looks like a thin, almost translucent, vibrating membrane floating in the air.
Wow.
The listener is literally seeing the physical weight of the sound waves.
Now, I want to clarify something here because the sources mention that for deaf audience members specifically, they aren't just getting the standard visual package. The system is actually triggering specific accessibility enhancements tailored for their experience, right?
That's a vital point. The AR language profiles allow for customized experiences based on the user's needs. For a deaf listener, the system activates a profile that automatically multiplies the harmonic environment intensity by 1.5.
So it basically turns up the contrast.
Yeah, it saturates those peripheral color shifts we just talked about. It ensures that the feeling of harmonic tension and release is unmistakably clear and impactful, compensating for the lack of auditory cues.
That's really smart.
It also adds a very distinct visual beat pulse to help firmly anchor the listener in the rhythmic drive of the piece. And perhaps most interestingly, it bridges the gap into the physical world.
The tactile seat sync. I was blown away by this when I read the research. Tell me about the seats.
So the concert hall venue seating is wired to the exact same network as the AR glasses. But it's not just a subwoofer bolted to the bottom of the chair, vibrating indiscriminately with the raw acoustic bass in the room.
Right, like at a movie theater.
Exactly. It's not that at all. The system triggers a highly curated tactile experience. The seat vibrates in precise, calculated sync with the structural architecture of the piece.
Oh, wow.
It emphasizes the foundational downbeats, the sudden, shocking accents, the rhythmic engine of the symphony. It turns the entire experience into a fully multimodal event. Sight and touch perfectly aligned with the score.
Which is just mind-bending.
Right.
But the visual layer doesn't stop at just colors, shapes, and vibrating chairs, does it?
It doesn't.
The glasses also provide textual wayfinding. They put actual words on the screen. And my immediate knee-jerk reaction to this when I read it was pure skepticism.
I think a lot of people feel that way initially.
I just thought, doesn't plastering text and colorful labels all over the stage completely ruin the magic of a live performance? I feel like I'd be reading a textbook while trying to watch a movie.
Yeah, no one wants that.
Right. I'd be staring at a floating word instead of watching the sweat drip off the cellist's nose during a huge solo.
It is a completely valid concern. No one wants an over-engineered, cluttered, heads-up display blocking a live human performance. But the designers address this through a rigorous philosophy they call the peripheral principle and the hierarchy of experience.
Okay, what does that mean in practice?
The absolute, unbreakable, fundamental rule of this AR architecture is that the digital layer serves the live performance. It never, ever competes with it. The text isn't a persistent, glowing Wikipedia article hovering in front of your face.
So how does it act, if not like a notification on a smartphone?
The designers describe it as acting more like a whisper in the dark. The text is incredibly minimal, and its placement is deeply intentional. For example, let's say we were deep into the first movement, and we reach bar 125.
Okay.
The musical structure shifts from stating themes to tearing them apart and exploring them. In the glasses, the words "development begins" just quietly, slowly materialize at the very bottom edge of your vision.
Like a subtle horizon line.
Precisely. It doesn't demand your attention. And later, at bar 375, when the piece is driving toward its conclusion, a small label reading "Coda" appears, along with a tiny wayfinder text that simply says, "Journey's End."
Journey's End. I really like that. It's very narrative.
It provides a sense of narrative distance in architecture. Notice that it doesn't show you a ticking digital clock counting down the seconds until the piece ends.
Yeah, clock feels cold, kind of mechanical. It would be stressful.
Exactly. Journey's End shows you the shape of the musical narrative. Furthermore, the text is specifically programmed to appear and dissolve in tandem with the music's breath. It fades in during structural transitions and fades out before the intense playing resumes.
And the sources detailed another layer of text called ghost visualizations, which I found to be maybe the most intellectually fascinating part of the whole visual symphony.
Oh, it's brilliant.
It doesn't just tell you the structure of Beethoven's writing, it comments on how the conductor is choosing to perform it tonight.
This is where the analytical domain of the system truly shines. At key interpretive moments during the performance, the listener might see a line of text quietly fade in that says, "Following the 1952 Furtwängler tradition," referencing a legendary, highly idiosyncratic past conductor.
That's so cool.
Or during a particularly heavy passage, the text might read, "Tonight, 20% slower than the composer's own marked tempo."
Think about what that accomplishes. It shatters the illusion that classical music is just a rigid museum exhibit being played exactly the same way for 200 years.
It makes it alive.
It elevates the listener's understanding. It reveals that the agonizingly slow tempo the conductor chose for that moment isn't just an inevitable fact of the sheet music. It's a living, breathing, risky interpretive choice happening right now.
Right.
By showing a ghost of a different possibility, the AR makes tonight's specific performance feel like a unique, unrepeatable artistic statement.
It invites the listener, regardless of their prior musical education, to become an active critic and participant in the interpretation.
Okay, I am completely sold on the beauty and the impact of this experience. The visual symphony sounds undeniable, but the logistical part of my brain is just screaming right now.
How does it work part?
Yeah, exactly. There's no magic without an engine room.
Yeah.
How does the headset actually know to do any of this? A digital file doesn't just naturally know what tension looks like, or when to pulse an amber light, or when to trigger a chair vibration. What is the actual script behind the magic?
So, to bridge the massive gap between a deaf listener's perception and the digital code running on the glasses, we have to look at the authoring language.
Okay.
Specifically, an architecture called ARML, the Augmented Reality Music Language. To give you a mental model, ARML is conceptually similar to something like MIDI show control, which lighting designers use to run lasers and strobes at giant rock concerts or Broadway shows.
Oh, I've seen that, like those massive light rigs.
Right. But ARML is entirely specialized for spatial, three-dimensional AR event authoring. And the core philosophical pillar of ARML is that it is score-centric and declarative.
I need you to unpack both of those terms for me. Score-centric and declarative. Let's start with score-centric. I assume that means it talks in the language of a musician, not a computer programmer.
That is correct. In standard computer animation, time is measured in clock time, seconds, and milliseconds. A programmer says, make the box red at 2.5 seconds, but ARML rejects clock time entirely. Time in ARML is always measured in musical measures and beats, bars and beats. Because a piece of music breathes, it speeds up and slows down, so the language maps strictly to the musical score itself.
That makes total sense. And what does it mean for a coding language to be declarative?
In computer science, an imperative language forces the programmer to write out the exact step-by-step mathematical instructions for how to achieve a result. Go to this memory address, draw a pixel here, move it by this vector.
Which sounds tedious.
It is. A declarative language simply allows the designer to describe what they want the end result to be, and the underlying engine figures out the incredibly complex math required to make it happen on the computer's graphics card.
So an ARML designer isn't writing thousands of lines of geometry math. They're just writing, show a mountain here when the brass plays loud.
Basically, yes.
Let's look at the actual document structure of an ARML file, because breaking it down really helped me understand the logic. It seems pretty intuitive.
It is remarkably elegant. Once you get past the standard header file containing the metadata, the composer, the piece, the venue, you encounter a block called the at palette.
The palette, like a painter's palette.
Exactly. This is where the visual designer defines the vocabulary of the piece up front. They define the specific hex codes for the ambertonic colors, the exact curvature of the geometric fate spike, the textures for dissonance. They build the paint box.
Then you move to the score map.
The score map is the scaffolding. It takes the abstract musical structure, movement 1, movement 2, the exposition, the coda, and maps it onto a digital timeline composed of those bars and beats we mentioned.
And finally, you get to the absolute heart of the system, the triggers. The triggers are the live wires. They are the conditional statements that listen to live music and fire the AR responses into the glasses. And looking at the syntax of these triggers, it's almost like reading a poem.
The simplicity is its strength. A visual designer can write a trigger as simple as onBR1. That command simply tells the engine, when the conductor hits the downbeat of measure 1, execute this visual event.
That is the exact line of code that cues our opening fate motif, that stark geometric spike, to appear.
Exactly. But RML's true power is that it goes infinitely deeper than just tracking bar numbers on a page.
Right. Because you can write a trigger based on music theory itself. You can write a command that says on harmony equals dominant seventh.
Yes. Think about the computational power behind that single line of text. The AR system is either analyzing the live harmonic data coming from the stage in real time or reading from a pre-encoded deep analysis of the score.
So it's constantly scanning.
Right. And the moment the orchestra arrives at a dominant seventh chord, which is a specific cluster of notes that creates a feeling of unresolved tension, the trigger fires instantly. It executes the command to flood the listener's peripheral environment with that pressurized blue-green color. The code itself understands harmony.
There is another trigger detailed in the sources that absolutely stopped me in my tracks when I read about it. The trigger is simply on silence.
Ah, yes. That trigger addresses a profound, almost philosophical musical concept. Audiences, especially casual listeners, often treat silence simply as a pause.
Right, a gap, an absence of music while you wait for the music to start again.
But a master composer like Beethoven treats silence as a deeply structural, highly active ingredient.
The space between the notes is just as important as the notes themselves.
Exactly. So how do you visualize an active silence? The ARML script can use on silence to trigger a visual representation of a fermata.
A fermata, for those who don't know, is
A fermata is a musical symbol telling the performer to hold a note or a rest longer than its written value, entirely at the conductor's discretion. When the orchestra hits a massive silent fermata, the AR glasses render it as a luminous, slowly expanding sphere of suspended time hovering over a pressurized visual void.
wow. It makes the silence visible as raw potential energy. A deaf listener isn't just sitting in the dark wondering if the song is over. They are watching the silence physically charge up like a battery before the orchestra finally releases the tension.
It is a stunning translation of intent. But to truly appreciate how ARML manages to approach time and musical structure so gracefully, we have to look backward.
Way backward.
We have to examine its intellectual grandfather. We have to rewind the clock to the year 1991 to an incredibly dense engineering standard called SMDL, the Standard Music Description Language.
It is genuinely wild to me to think that the foundational logic running a 2026 augmented reality headset experience was debated and laid out in a 1991 IE document before the modern internet even existed.
It is a testament to brilliant systems engineering. SMDL was an application of an earlier hypermedia standard called HighTime, which itself was based on SGML.
SGML.
If SGML sounds familiar, it's because it's the parent language that eventually gave birth to HTML, the language that builds every website on the internet today.
Oh, wow.
Yeah. The ANSI working group, the American National Standards Institute that developed SMDL in the early 90s, realized something profound about trying to put music into a computer. They realized you cannot represent music effectively as a single flat file.
Why not? Like, why couldn't they just make a music.doc file?
Because music has too many conflicting identities. Is music the ink printed on the page? Is music the abstract mathematical sequence of pitches in the composer's head? Or is music the physical sound waves generated by a violinist sweating on a stage on the Tuesday night?
I mean, it's all of them, really.
It's all of them. So the SMDL architects established that to encode music for computers, it must be rigidly separated into domains.
I really want to unpack these domains, because understanding this separation is the master key to understanding how the AR glasses work. The first domain they established is called the cantus.
The canvas is the purely logical domain. It is the absolute abstract musical information that represents the core DNA of the composer's intent.
Just the math of it.
Exactly. If you take Beethoven's Fifth Symphony, the cantus only contains the sequential mathematical data. Pitch X is followed by pitch Y, and pitch Y lasts twice as long as pitch X. That's it.
It's completely agnostic to the real world.
Entirely. The canvas doesn't know what an oboe sounds like. It doesn't know what a treble clef looks like. It has no concept of a page turn. It is just the raw, logical DNA.
This makes so much sense when you think about sheet music. If a composer writes a really low part for a French horn, they might print it on the page in the bass clef, or they might print it in the treble clef using a bunch of ledger lines below the staff. To the musician, it looks completely different visually.
Right. Visually, it changes.
But it is the exact same piece of music. The pitch hasn't changed. So the clef, the visual formatting, doesn't belong in the cantus. It belongs in the second domain, the visual domain.
Precisely. The visual domain handles all the scoring information. It dictates the page layout, the font choices for the dynamics, the printable editions for the publisher. The computer keeps the visual representation completely separate from the logical data.
Which brings us to the third domain, the gestural domain.
The gestural domain is the performance information. It is the actual real-world acoustic rendering. It contains the data about the physical plucks of the strings, the breath of the oboist, the slight human variations in microtiming and volume that a specific performer on a specific night brings to the piece.
Okay, let me try out an analogy here to make sure I have this locked in. Tell me if this tracks.
Let's hear it.
The cantus is the script of a play, the raw dialogue and plot written by Shakespeare. The visual domain is the physical paperback book you buy at the store with its specific font and cover art. And the gestural domain is the actor actually performing that monologue on a stage with all their specific pauses, shouts, and tears.
That is an absolutely perfect, flawless analogy. The script, the book, the actor, and to complete the SMDL standard, they included a fourth domain.
The analytical domain.
What does that one do? This was envisioned as a playground for musicologists and theorists. It allowed them to attach metadata, commentary, harmonic analysis, and thematic tracking to the cantus without altering the original work.
Wait, the analytical domain. That is exactly what our AR system is doing. It is pulling from a deeply encoded analytical domain to know when a specific theme is returning, or to flash Furtwängler's name as a ghost visualization on the AR lenses.
You've connected the dots perfectly. The ARML script running the glasses today is essentially a massive real-time query against the analytical and Cantus domains, rendering the results into a new spatial domain. But the true genius of SMDL, the thing that makes live AR synchronization possible 35 years later, is how it handled the concept of time.
Because clock time doesn't work for music.
No, it doesn't. In SMDL, the Cantus does not use seconds, minutes, or milliseconds. It uses an abstract coordinate system based on virtual time units, or VTUS.
Which is necessary because if a composer writes a piece at 60 beats per minute, a live orchestra almost never plays it at exactly a mathematical 60 BPM.
Right. Humans aren't metronomes.
They might play it at 62 or 58, depending on the acoustics of the hall, the mood of the conductor, or how much coffee the percussionist drank that morning.
Exactly. Human performance is inherently elastic. Real-time clock measurements are useless for representing abstract musical flow. So SMDL defined a virtual coordinate space where the rate that time passes is controlled by a construct they quite literally named a baton, a direct metaphor for the conductor's physical stick.
It is so clever.
The digital baton contains tempo directives that scale those abstract virtual time units into real ticking clock time. And they also created constructs called wands, which were tools to apply modifiers like filtering or articulation to a schedule of events.
Now, this brings up a huge logistical question. It's the primary pushback my brain had when I was trying to wrap my head around this whole architecture.
What is it?
If the AR system uses a script based on virtual time and relies on an engine to map it to real time, how on earth does it handle extreme human unpredictability during a live concert? Let's go back to that fermata, that moment of active silence.
Right, the floating sphere.
What if the conductor decides, entirely in the moment, driven purely by raw emotion, to hold that silence for an agonizing 10 seconds instead of the usual 3? How does the visual rendering engine in the AR glasses not just keep marching forward, assuming the beat continued, and completely desync from the orchestra? You'd have visuals firing wildly out of time with the music.
That scenario is the ultimate nightmare challenge of live AR synchronization.
It seems impossible to account for.
But the solution is found in AirMel's incredibly robust affirmative protocol and specific live triggers like on-conductor gesture. The AR system is not just blindly playing back a pre-recorded timeline like a movie projector. It is highly reactive.
How reactive?
The venue utilizes infrared motion capture cameras pointed at the conductor's baton, allowing it to override strict digital timelines.
Wait, so the computer system is literally watching the conductor in real time?
Yes. The ARML script dictates that the synchronization protocol uses OSC, Open Sound Control, which is a high-speed networking protocol. It ingests the literal physical beats from the motion-tracked conducting baton.
So it's synced to the human movement.
Exactly. If the conductor slips up, there's a fallback to a click track or a human stage manager, but primarily it follows the baton.
Walk me through the exact sequence of events when that fermata happens.
When the conductor reaches that massive silence and wants to hold it, they stop moving the baton in a rhythmic, metric beat pattern. They hold the baton suspended in the air.
And the cameras see that.
The motion capture system reads this. The AirML trigger on-conductor gesture, or fermata, fires instantly. The visual rendering engine receives this command and physically pauses the forward motion of the digital timeline.
It just freezes.
This allows that glowing visual sphere of silence in the glasses to expand indefinitely for 3 seconds or 10 seconds, waiting in a state of suspended animation until the motion capture system registers the sharp downward release gesture from the conductor.
That is just staggering. And it proves why SMDL's foresight in 1991 to rigidly separate the abstract logical sequence of notes from the real-time gestural rendering was so brilliant. It perfectly anticipated this need to pause time.
It is the foundation that makes the entire illusion possible.
I think we've reached a natural pivot point here. We have the ARML script.
Sure.
We understand the logic, the domains, and how the system handles the elasticity of human timing. But how do we bridge the massive gap from that invisible text script running on a server to the actual, physical, real-time 3D projection beaming light directly into the retinas of the audience members.
We need to go down into the engine room.
Exactly.
To understand the engine room, we have to look at the modern web development stack. The heavy lifting here is being done by a browser API called WebXR.
Let me make sure I had my acronym straight. WebXR is the modern framework that essentially replaced the older WebVR standard, correct?
That is correct. WebVR was an older API designed purely for virtual reality. Virtual reality is characterized by complete occlusion. You put on a headset, the screens go dark, and you are entirely shut off from the real physical world placed inside a digital one.
Like playing a VR video game.
Right. WebXR, however, was built from the ground up with a much broader scope. The X stands for extended. It handles both VR and augmented reality under one unified interface. For our concert scenario, the audience's glasses are running a WebXR session in a specific mode called Immersive R.
And Immersive R means the screens and the glasses are transparent. The digital content is drawn on top of the real world. So the orchestra, the conductor, the velvet seats, the person coughing next to you, they all remain perfectly visible. The digital geometry is just layered over them.
Exactly. But layering 3D graphics over the real world introduces a terrifying computational challenge: spatial anchoring.
Because if the system decides to draw a glowing halo over the cello section, and I turn my head to sneeze, that digital halo cannot swing wildly across the room attached to my eyeballs. It has to look like it is physically bolted to the floorboards where the cellos are sitting.
Right. If the graphics swing with your head movement, the illusion is completely destroyed. And more importantly, your brain's vestibular system will violently reject the input.
You'd get dizzy.
You will experience immediate severe motion sickness. To prevent this, the WebXR API leans heavily on the headset's internal tracking hardware. Every single time the screen draws a new image, which is happening between 72 and 120 times every single second, WebXR calls a function named xrframe.getViewerPose.
What does that function actually do in that fraction of a millisecond?
It asks the hardware sensors, where exactly is this person's head looking right now down to the millimeter? It calculates the listener's exact physical position in the room and the rotation of their skull. It returns this data as a mathematical construct called a 4x4 transformation matrix.
Okay, stop right there. 4x4 transformation matrix is heavy math jargon. Explain that to me like I'm 5 years old. What is it actually?
Think of it like a highly specific set of instructions for a robotic camera arm. Imagine you want to describe how to move an object from the center of a room to a specific corner, tilt it up, and shrink it.
Go
You need 3 types of instructions: translation, which is moving it left, right, up, down; rotation, which is pitch, yaw, roll; and scale, making it bigger or smaller. A 4x4 matrix is just a standardized grid of 16 numbers that perfectly encodes all of those instructions simultaneously.
So the headset calculates this 16-number grid based on my head movement 120 times a second.
Yes, and the 3D rendering engine applies that grid to its virtual camera. It instantly shifts the perspective of the digital world exactly opposite to your physical head movement. That math is what keeps the geometric spikes locked firmly over the stage while you look around.
Okay, so WebXR is the display manager. It handles the screens and the tracking. But what is the actual artist? What software is drawing the millions of polygons and colors that make up these geometric mountains and shimmering halos?
Good question.
Because the sources dive into a big debate between 3 different web technologies: A-Frame, Raw WebGL, and 3JS.
It's a classic software engineering trade-off between ease of use and raw performance. Let's start with A-Frame. A-Frame is a fantastic web framework that allows developers to build 3D VR scenes using a syntax that looks almost identical to standard HTML.
So like writing code for a normal website, you just type box instead of P for a paragraph.
Precisely. It is incredibly easy for beginners because it relies on the DOM, the document object model. The DOM is the standard structural hierarchy that all web browsers use to organize text and images on a page.
If it's so easy, why aren't they using it for the AR Symphony?
Because the DOM is fundamentally a bureaucracy, and it has a strict performance ceiling. Imagine an office building where every single time an employee wants to move their desk an inch to the left, they have to fill out a form, send it to HR, have it approved, and filed. That's the DOM. Updating an HTML attribute in real time adds significant computational overhead.
Which is fine if you're just moving a single 3D box around.
Right. But in our Symphony, we are trying to render thousands, potentially millions, of individual digital particles that are all rapidly reacting to complex audio frequencies simultaneously. The DOM bureaucracy simply cannot handle that volume of high-frequency data updating. The frame rate would completely tank, the visuals would stutter, and the audience would get sick.
So if a frame is too slow, why not go all the way to the other extreme and write the graphics engine using raw WebGL? Go straight to the metal.
Because raw WebGL is brutally, punishingly complex. WebGL is a low-level API that talks almost directly to the computer's GPU, the graphics processing unit.
It's just hard to code.
It doesn't understand concepts like cameras or lights or mountains. It only understands massive arrays of raw numerical coordinates and memory buffers. To instruct raw WebGL to draw a single, unlit, completely stationary 3D cube on a screen requires a developer to write roughly 200 lines of incredibly dense boilerplate code just to manage vertex arrays and compile basic math.
Wow. No one wants to spend a week writing 200 lines of code just to see a gray box.
Exactly.
Yeah.
Which brings us to the sweet spot. 3JS. 3JS is a high-level JavaScript library that sits directly on top of WebGL as an abstraction layer. It gives developers 95% of the raw, blistering performance of WebGL, but it hides all the bureaucratic pain. In 3JS, you can create a scene, add a digital spotlight, and draw that same cube in about 5 simple lines of code.
It bridges the gap between human logic and GPU power.
Yes. And crucially, for our Symphony, it has built-in performance optimizations, like a feature called Instance Mesh. This allows the engine to draw 10,000 identical objects, say a massive swirling cloud of digital particles representing the violin section sound, with only a single draw call instruction sent to the GPU. It avoids the CPU bottleneck entirely.
That makes perfect sense.
Yeah.
But we also have to talk about how these shapes behave. Because the geometry we're seeing in this AR symphony aren't just static boxes sliding around. The sources describe them as organic. They are breathing, bulging, mutating, and throbbing in time with the music.
Right. They feel alive.
How does 3JS make a geometric shape look alive?
That illusion of life is handled by microscopic programs called shaders, and they are written in a specific language called GLSL, the OpenGL shading language.
What makes a shader different from a normal program?
A standard computer program runs on the CPU, the central processor, which calculates things sequentially, one after another, very fast. A shader runs directly on the graphics card, the GPU.
So it's doing multiple things at once.
The GPU is designed for massive parallel processing. It can calculate the math for 1 million individual pixels or vertices at the exact same fraction of a second. There are 2 main types: fragment shaders, which calculate the precise color of every pixel on the screen, and vertex shaders, which manipulate the actual 3D physical geometry of an object before it's drawn.
The sources gave a really illuminating example of a vertex shader that uses a variable called a uppulse uniform. Can we walk through exactly how that works?
Absolutely. The term uniform simply means a variable piece of data that the main JavaScript program passes down into the shader program on every single frame. It's a bridge between the logic and the graphics card. In our AR scenario, the main JavaScript program is constantly analyzing the volume and intensity of the music from the ARML script. Let's say the timpani drums are playing a massive roll that is getting louder and louder.
A crescendo.
Right. The main program calculates the intensity of that crescendo as a number, say between 0 and 1, and passes that number into the vertex shader as the uppulse uniform.
And what does the vertex shader do with that number?
The vertex shader takes that uppulse value and physically pushes every single vertex, the corner points of the 3D shape, outward along their normal axis. So as the timpani gets louder, the uppulse value increases from 0.2 to 0.8, and the mathematical shape representing the drums literally bulges and breathes outward in perfect microsecond sync with the audio.
It is a direct mathematical translation of acoustic energy into physical geometric displacement.
It's breathtaking to watch. But this brings up the final critical piece of the engine room puzzle, the streaming architecture.
Right.
We have the ARML script running on a server. We have the 3JS rendering engine and shaders running on the glasses. How does the data actually travel through the air from the conductor's podium to the glasses in real time without lagging?
The technical setup for the venue is intense. They are running a Node.js server. Node is a runtime environment that handles back-end network traffic really efficiently. This server ingests the live data from the stage, say 32 separate tracks of NIDI data representing all the different instrument sections, but doesn't try to beam 32 chaotic streams of data to every pair of glasses in the room.
That would congest the network instantly.
Instead, the Node server flattens it. It calculates the absolute timestamp of every single note and trigger event across all instruments, sorts them chronologically into one giant, highly organized, flattened event list, and then streams that single list out to all the connected headsets. And it uses a technology called WebSockets to do it.
WebSockets are absolutely vital here. A traditional web request works like a phone call where you hang up immediately. Your browser asks the server for an image, the server sends the image, and the connection is closed. If you want another image, you have to initiate a brand new call.
which introduces latency.
Massive latency. WebSockets create a persistent, open, two-way tunnel between the server and the AR glasses. The connection stays open. The server can push trigger data to the glasses instantly, the millisecond it happens, without the glasses having to constantly ask, is there a new note yet?
But even with a blazing fast WebSocket connection, the real world of networking is messy. Wi-Fi signals fluctuate. 1,000 people in a room with smartphones causes interference. The raw data arriving at the glasses will inevitably have micro stutters and jitters.
Oh, without a doubt.
If you map that raw, jittery data directly to the visual size of a mountain, the mountain is going to violently glitch and twitch on the screen. It would totally ruin the organic majesty of a symphony.
It would look like a broken video game. So the developers solved this network jitter through a genius client-side mathematical technique called interpolation, specifically a function called lerping, which stands for linear interpolation.
Let's break down lerping. Let's say a massive brass chord hits on stage. The WebSocket data tells the glasses that the target size for the visual mountain should jump instantly from a size of 1 to a size of 10.
If the Three.js rendering engine just blindly followed the raw data, the visual mountain would instantly teleport from size 1 to size 10 in a single frame. It would feel robotic and harsh.
Very unnatural.
Instead, the rendering loop looks at the current state, which is 1, and the new target state, which is 10. On the very next frame, it doesn't jump to 10. It calculates a fraction of the distance, say 10%, and moves to 1.9. On the next frame, it moves 10% closer to the target again.
So it smoothly glides up, 1, then 3, then 6, 8, 10. It smooths the transition out over a few milliseconds so it feels like a fluid, organic breath rather than a digital snap. Think of it like a car accelerating smoothly from a stoplight rather than instantly teleporting to 60 miles per hour.
Precisely. And the key is that the Three.js visual animation loop is running at 90 or 120 frames per second, completely independently of whenever the WebSocket messages happen to arrive. It just continually lerps toward whatever the most recently received target value is.
So it hides the lag.
By separating the arrival of the data over the network from the rendering of the data on the screen, the visual experience remains perfectly smooth and buttery, even if the venue's Wi-Fi hiccups for a fraction of a second.
It's an incredibly robust architecture.
Yeah.
And honestly, listening to us describe WebXR, node servers, massive parallel GPU shaders, and WebSocket streams, the whole system feels impossibly modern.
It feels very futuristic.
It feels like science fiction from 10 minutes in the future. But as we pivot into Section 4, the historical roots of the deep dive, it becomes clear that the intellectual grounding for all of this spatial tech actually goes back decades. To really appreciate what we're doing in 2026, I want to talk about a piece of software from the 1980s called Diversitune.
The Versatune is a phenomenal historical artifact. It was a music program built for the Apple IGS personal computer. To put the sheer technological constraints of the era into perspective, the standard memory configuration for an Apple IGS when it shipped was just 512 kilobytes of RAM.
512 kilobytes. Today, a single, completely average, high-resolution photo taken on your smartphone is often 5 to 10 megabytes. The Apple IGS had a fraction of the memory of a single photo.
It was virtually nothing by modern standards. So the engineering question was, how on earth do you manage, record, and play back complex multi-track music on a machine with so little brain power?
You couldn't just record the audio like a tape recorder, right?
No, absolutely not.
Ah.
Before digital protocols like MIDI, if you wanted to record music digitally, you had to sample the actual analog audio waveform. Sound waves take up massive amounts of storage space. Furthermore, if you tried to overdub, recording a new track on top of an old track, you ran into the sound-on-sound problem.
The quality would just degrade.
The analog tape hiss and background noise would multiply with every layer, degrading the audio quality until it was unlistenable mud.
But the Diversitune sidestepped this entirely by changing the fundamental definition of what they were actually recording. Diversitune didn't record sound at all. It acted like a digital player piano. It only recorded the physical actions of the musician.
Exactly. It recorded which specific piano key was pressed, exactly when it was pressed, and how hard the key was struck, a value known as velocity. It was essentially implementing the SMDL separation of domains years before the standard was formalized.
Ah, so going back to the cantus.
It separated the cantus, the tiny bytes of data representing the idea of what notes to play, from the rendition, the synthesizer hardware chip inside the computer that actually generated the audio frequencies.
Because it was only saving numbers, you could record 32 wildly complex tracks of data perfectly in sync, and it barely took up any disk space. And the audio quality never degraded because the computer was just reading instructions to the synthesizer fresh every time you hit play.
It was an elegant solution to a harsh hardware limitation.
But the part of the Diversitune story that absolutely blew my mind, and the reason it connects directly to our modern AR Beethoven experience, is their implementation of the classic bouncing ball algorithm for adding sing-along lyrics to music.
This is a brilliant, totally forgotten piece of historical problem solving. Think about a karaoke screen. If you want to make a sing-along video, how do you mathematically program a visual, the bouncing ball, to land perfectly on the text of the lyric at the exact millisecond the vocalist sings the word?
The software manual for Diversitune explains the process, and it sounds like agonizing, painstaking manual labor. First, the user had to open up an AppleWorks word processor document and type out all their lyrics. Then they had to manually go through the text and type a backslash or a reverse hyphen directly into the middle of every single syllable of every word to create a digital target marker.
They were manually formatting the cantus for a visual overlay.
Right. Then they loaded that text file into Diversitune, hit the record button, listened to the song playback, and literally tapped the physical keys on the computer keyboard rhythmically in real time to assign the timings to their syllables.
The ergonomics of it are fascinating. The user would rest 3 fingers on the comma, period, and slash keys on the keyboard. Pressing the comma and period keys advanced the ball to the next word in the lyric sheet, while tapping the slash key made the ball bounce in place repeatedly on the same word for a held note.
It sounds like playing a primitive rhythm video game. But here is the absolute genius part of the manual. The developers wrote a note addressing an anomaly the users would experience. They warned users that while you are actively recording your taps live, the visual ball on the screen just teleports from word to word. It doesn't draw a smooth bouncing arc.
Right, because it can't.
Exactly. Why? Because to draw the physical arc of a ball flying through the air, the computer's animation engine has to start drawing the upward motion before the beat actually happens. The computer has to know the beat is coming in the future, so the visual ball can lift into the air, crest, and land perfectly on the downbeat.
And when a human being is tapping a keyboard live, the computer cannot see the future. It has no idea when your finger is going to come down for the next tap, so it cannot calculate or animate the anticipatory arc. But once the track is recorded and saved during playback, the computer can read the whole file. It can look ahead.
And the manual goes even further. It gives advice for people trying to sync the bouncing ball to a song playing on an external CD player that isn't digitally connected to the computer. It literally tells the user to press the play button on the computer a fraction of a second before the beat hits on the CD. The manual explicitly states that the ball must lead the song just a little.
That realization right there is profound.
It is, because that 1980s logic, the fundamental realization that for a visual to feel synchronized to an audio event, the visual animation must physically anticipate the beat, is the exact identical logic needed in 2026 to prevent AR visuals from perceptually lagging behind the orchestra.
Yes. That is exactly why the voice highlighting pre-glow of anticipation we discussed an hour ago is so neurologically vital. If the visual explosion of the AR geometry only begins to render on the screens at the exact millisecond the acoustic sound wave from the brass section reaches the listener's eardrum, the human brain will process the visual as being late.
Because the visual data takes time to process.
The visual processing system must lead the auditory processing system just a tiny bit for the brain to fuse them into a single, perfectly coincident synesthetic event. The developers of Diversitune solved this perceptually with a bouncing ball 40 years ago.
It is incredible how these problems just echo through time. And it goes back even further than Apple computers in the 80s. If Diversitune solved the problem of temporal synchronization, another pioneer named John Whitney Sr. solved the problem of visual geometry.
John Whitney Sr. is a towering figure. He is widely considered by historians to be the godfather of algorithmic visual music and motion graphics. And his primary tool of creation in the 1950s, 60s, and 70s was utterly fascinating. He wasn't using digital processors. He was buying surplus, repurposed World War II mechanical anti-aircraft, targeting computers and using them to create art.
Wait, we really need to pause on this because it sounds absurd. A mechanical anti-aircraft computer.
It's true.
How does a machine made of gears calculate where to shoot a gun, and how on earth does an artist turn that into a visual symphony?
It is one of the great stories of 20th century technology. During the war, militaries needed to shoot down enemy planes moving at high speeds. To hit a moving target, you have to aim ahead of it. You have to calculate the plane's speed, trajectory, wind resistance, and the velocity of your own artillery shell.
That's a lot of math.
You are essentially solving incredibly complex differential calculus in real time, but digital microchips didn't exist, so they built mechanical analog computers. These were massive, heavy boxes filled with precisely machined gears, rotating shafts, cams, and linkages.
So the math was physically represented by the metal.
Exactly. The speed of a rotating steel shaft represented a mathematical variable. The physical interaction of the gears solved the calculus continuously. John Whitney Sr. bought these surplus war machines, gutted the weapon systems, and connected the rotating output shafts to control the movement of a camera and lights over photographic film. He was using military targeting calculus to draw perfect, infinitely complex mathematical curves on film.
Taking a machine explicitly designed to tear metal and human bodies out of the sky and rewiring it to draw beautiful, peaceful, abstract art. That is incredibly poetic. And through this work, he developed a theory he called differential dynamics, which is the exact mathematical principle governing how our AR glasses render harmonic tension and release today.
Whitney's fundamental insight was about the aesthetic and mathematical relationship of moving points over time. He observed that if you have a collection of points moving at integer ratio speeds, speeds that are simple, clean mathematical multiples of each other, like 2 to 1 or 3 to 2, they inevitably cross paths and create emergent, recognizable, highly organized, harmonious patterns. This is the visual equivalent of consonance.
But if you change those speeds slightly so they don't lock into ratios,
If they move at non-ratio, irrational speeds, they create visual chaos. They never align. The resulting shapes are tangled, unpredictable, and tense. This is visual dissonance. Whitney believed deeply in a concept he called complementarity.
meaning they complement the audio.
He wasn't trying to just make shapes bounce to a beat. He was trying to establish a true, objective visual counterpart to musical harmony. He was obsessed with Lissajous figures, which are complex, sweeping patterns traced by intersecting sine waves. By drawing these figures, he was essentially drawing the physical geometry of sound waves.
But Whitney, for all his genius, was fundamentally limited by his medium. He was projecting these brilliant, multidimensional equations onto flat, two-dimensional movie screens. You watch them from a distance. But in our modern VR and AR scenario in the concert hall, the deaf listener isn't watching a flat movie screen at the front of the stage. They are standing inside these three-dimensional, volumetric, Lissajous sculptures.
It is the ultimate final realization of Whitney's life's work. The audio frequency ratios generated by Beethoven's score are directly driving the X, Y, and Z oscillation frequencies of millions of GPU particles entirely surrounding the listener.
So when the symphony enters a dark, tense state of harmonic dissonance, the listener is physically enveloped by a writhing, unstable, chaotic geometry. The math is literally unresolved all around them.
And then the payoff. When the orchestra finally resolves harmonically, when the tension breaks and they hit that pure, perfect, resonant major chord, those thousands of chaotic swarming particles suddenly miraculously converge.
The tension breaks.
The mathematical ratios lock into integers. The particles snap into beautiful, perfectly stable, crystalline architectural forms right in front of the listener's eyes. You don't just hear a cadence. You literally walk through a harmonic convergence as it physically solidifies in the air around you.
It takes Whitney's theoretical concept of a visual cadence and gives it true physical volume and mass. It is a staggering achievement. Which brings us to a really important final point regarding the emotional fallout of all this technology. Because when I first read the pitch for this, putting AR headsets on audience members at a classical concert, my biggest worry was isolation.
How so?
Well, you go to a live concert to be with other human beings. You go for the collective effervescence of a crowd. Doesn't surrounding a person with a personal, glowing tech bubble inherently isolate them from the rest of the audience? Don't they just retreat into their own private screens?
It is a deeply valid concern, and it's the trap that VR often falls into. But the system design of this AR experience turns that isolating paradigm entirely on its head through a feature they call real-time emotional mapping. It doesn't isolate the user. It creates a shared visual layer based on the aggregate, real-time emotional response of the entire physical audience.
The sources refer to this as opt-in anonymous biometric reporting. Explain how that works in the hall.
The AR glasses themselves, or the connected smartwatches on the wrists of the audience members, contain biometric sensors. They can measure heart rate, skin conductivity, and general arousal levels. Any audience member who chooses to opt in can allow their data to be anonymously aggregated by the venue's server during the performance. And crucially, this data is not gamified. It's not a scoreboard showing who is having the most fun.
Right, the designers specifically referred to the visualization as creating weather in the hall.
That's a beautiful way to describe it. It's a gentle, diffuse, shared visual environment. Let's say the cellos hit a particularly agonizing, tragic, beautiful melody in the second movement. As that emotional wave sweeps through the physical crowd and hundreds of human heart rates simultaneously synchronize or elevate collectively in response to the art, the AR system reads that massive biometric shift.
And what happens visually?
In response, a warm, soft luminescence literally rises up into the shared AR space floating above the audience.
Think about how profound that is. You can physically, visually see the private internal experience of being moved by art becoming a shared public revelation. If you're wearing the glasses, you discover instantly that you aren't the only one holding your breath in the dark. It actively closes the gap between strangers.
It visualizes empathy. And philosophically, this technology closes an even larger, older gap. When you step back and look at the whole system, this AR architecture acts as a massive, real-time compression algorithm for musical education.
Oh, I completely agree. Because traditionally, classical music has a massive barrier to entry. If you truly want to understand the thematic DNA, the harmonic architecture, the historical context, and the interpretive nuances of a piece as massive as Beethoven's Fifth, you need decades of study.
You absolutely do.
You need to know how to read complex orchestral scores. You need years of critical listening. You need a deep background in music theory. It can be elitist.
This AR system completely democratizes that profound understanding. It takes complex musical structure that was previously only accessible intellectually, locked behind years of academic study, and translates it into an intuitive, biological, visual language that you can physically inhabit and feel in real time, zero prior experience required.
That, to me, is the ultimate takeaway of this deep dive. Picture our concert hall again. You have a deaf listener who has literally never heard a single acoustic note of music in their entire life, sitting shoulder to shoulder with a 60-year-old expert musicologist with a PhD from Juilliard.
Side by side.
They are sitting side by side. The downbeat hits. And through this incredible spatial, visual, and tactile translation, they both fundamentally deeply understand the architecture of Beethoven's Fifth Symphony at the exact same time. They both physically feel the tension build in their periphery, they both visually recognize the evolution of the themes, and they experience the massive cathartic release together.
The technology doesn't replace musical feeling with cold intellect. It does something much harder. It delivers the intellect precisely at the millisecond it most enhances the feeling. It traverses the massive gap between the composer's interior abstract world and the audience's visceral experience in a single evening.
Okay, let's pull all of these incredible threads together. We started in a hushed concert hall, visualizing a deaf listener experiencing the legendary opening spike of fate in Beethoven's Fifth Symphony. We peeled back the digital curtain to see how score-centric ARML triggers interact with 3JS shaders and WebXR transformation matrices to make that breathing 3D geometry possible.
It's an incredible stack.
And we traced the deep, fascinating historical roots of that technology all the way back to the logical domains of the 1991 SMDL standard, the painstaking bouncing ball anticipation of Diversitune in the 1980s, and the beautiful differential dynamics of John Whitney repurposing anti-aircraft computers.
It is a stunning testament to how human ingenuity across generations continues to find new, ever more immersive ways to map, understand, and share our most profound artistic expressions.
It really is. And I want to leave you, our listener, with a final, slightly provocative thought to mull over as you go about your day. We spent this entire hour talking about how we have finally perfected the technology to map the emotional and structural architecture of existing classical music perfectly into visual and 3D space.
Right.
The visual is entirely serving the audio. Beethoven came first, the AR came second. But this new spatial visual language is now so robust, so computationally powerful, and so universally capable of conveying tension, release, rhythm, and raw emotion without a single sound.
Where are you going with this?
How long will it be before a new generation of artists emerges who completely flip the script?
What do you mean?
I mean composers who write symphonies, intended to be seen and felt first. where the architectural volumetric visual masterpiece floating in the room is the primary text of the art, and the audio we hear is acting merely as a supportive secondary accompaniment to the visual journey.
Wow. You're talking about the birth of a true native visual music.
Exactly. We might be watching the birth of an entirely new medium.
Hmm.
Until next time, keep diving deep.